Let us continue from the first part. Okay. Let us look at your strength of material now and 5. Okay. Stress and strain. When a beam is subjected to the load, the beam will experience the stress. I mean, this will take you as well, give you the example from your static. You are having the forces acting on your beam. Forces acting, your beam, this beam will experience the stress as a result of what of the force. That region there where the force has been applied, it will experience what? The stress. If the applied load causes stress to go beyond the maximum safe stress and exceed the limit of elasticity, it can cause the failure. Remember the stress and strain graph that we dealt with about? It went beyond the safety factor, then it fractures, it fails you. Now, under your beams, you are having your beam supports, then you are having the force applied, then you are having something like this. Then where the maximum bending moment occurs, that's a critical point. This part as well, this statement as well, it is applicable to that critical point. If if the load causes the stress to go beyond, if it goes beyond, your beam will break. Your beam will always break at the maximum bending moment. Okay, that's where the critical point is. Okay, but those will deal with them later on. Right. Then the third statement said to limit this failure, we have to know the strength of different materials and how they are obtained. Now, this is where we get the strength of material under that tangent line, where the limit of proportionality, upper yield, lower yield, the fracture. This is where we get the strength of material under. That's where we get strength of material, where Hooke's law is. Now we use Young modulus to determine the strength of material. Now this point, it indicates to this part of the region of your stress and strain graph. To determine the different strength of materials, they are subjected to tests such as, on the first video I've already indicated the tensile test and the compressive test, it is one the same thing. Then you are having the shear stress. The shear stress, obviously, they are either it's your beam, then they are having force cutting your beam into two. Then you are having the hardness of test, you are having the impact test, the fatigue test. Now, these are the tests that they will do in determining the strength of any material. And this is your exam, it's a possible exam questions. You need to know this 6 testing that we do to test the strength of material. You need to know this 6 testing: the tensile test, compressive test, shear test, hardness test, the impact test, and the fatigue test. Now, this one, in your books, you need to study it, how it's been made. Because in exam, they can say, describe the tensile testing. And another one that you need to know how to describe it, it is the hardness test. You need to know how to describe the hardness test. And another one, it is but normally on fatigue, but you'll never know this examiners. But this 3, you need to know how to explain those tests, how are they made. And I want to believe that your books, they do have those descriptions. Right. We use the above test to determine the strength of material, like I said. Now, let us then define stress. Is an internal reaction of the cross-sectional area as a result of the applied force. Okay, when the force has been applied on this material, the cross-sectional area, it will counteract the applied force. That's what we call stress. Now, how do we calculate stress? This is the formula that we will be using to calculate what stress. Our stress would be force over area. The SI unit, it is Pascal. Okay, now we are having different types of stresses. I know that in N4 we only dealt with the stresses tensile, compressive, and shear stress. Now, you are now in N5. We have what we call bending stress, or direct stress, I mean to say. We have bending stress and the shear stress. And another stress that we have, it is the torsion stress. We have different types of stresses, torsion stress, and of each torsion stress, we'll deal with it when we are doing the drives. Okay. Now, direct stress, this is what you need to know about the direct stress. Direct stress consists of tensile, or it consists of compressive force. What tensile direct stress can either be tensile stress, or it can be compressive stress as a result of the force applied. The force directly applied on the material, then you get what the stress as per the description of the force applied. If it is the tensile, you'll get the tensile stress. Compressive, you'll get the compressive. That is the direct. Then the bending stress, this one, it is the combination of two things. It is the combination of force compression and the force tensile. It occurs, this is your beam, this is your beam. You are having forces acting on your beam, then your beam gets to bend this way. Now, this is what you'd realize as your beam bends that way. You'd realize that inside your stress, you are having forces converging, where here at the critical point. It then means inside that a beam, we are experiencing force compression as a result of what? Of those forces converging towards the critical point. Now look at the outside. The outside, you are getting what? Stress tensile. Because you are having forces pulling away from the material, then you get what? The force, the stress tensile. That means the bending stress, it is the combination of compressive and tensile force. That is why when you are doing, I think, simple bending of beams, you will then be asked to draw the stress, the bending stress graph. You will draw this bending stress graph from this description that I gave you here. Okay, but we'll deal with that later on. Then we are having the shear stress. Now you need to know these types of stresses that we have. It is your possible exam question. Give us 3 types of stresses, or give us 4 types of stresses. It will be direct stress, bending stress, shear stress, and the torsion stress. Okay, and the torsion stress. It will depend with the given information. Now, let's look at the strain. Strain, when the object is in the state of stress, deformation will take place. Therefore, strain, it is the deformation of the material under stress. Like I said, when the change of material starts to, when the material starts to experience the change, that change we call it deformation. We call it what? Deformation. Now, how do we then calculate the strain? In calculating the strain, it is strain equals to the change in length over L original. No SI unit, because the meter and the meter will cancel out. Now, let's look at the shear stress. I left it for a reason. Let's look at the shear stress. What is the shear stress? Shear stress, it is the force that cuts the beam into 2 states. It is the force that cuts beam. This is your 0. It is the force that cuts your beam into 2 states, from the positive state to the negative state. That is your shear force. Okay. Shear stress, it is denoted as a tau. This funny symbol as T. It is called tau. Shear stress will develop in material when the slide is taking place, like the below diagram, like this below diagram. Okay. To calculate the shear stress, it is important to remember that the shear area must be considered, meaning this is the formula that we'll be using to calculate the shear stress. Now, it is force over area. Now, you are having metal plates joined, let's say by a rivet, then there's a force tensile applied there. You will realize that this pin will experience the shear stress there, because as they are pulling that force there, this pin will experience the shear. This is the single shear. This is the single shear stress. Okay. Then let's say you are given same metal plates. They are joined together by rivets. Right. Then you are having that rivet there, the pin. Okay. Now this is what you would realize here. Now you are having force applied on the first metal plate. You are having force applied on the second metal plate. Now this is what you will realize here. This is what you will realize that this pin will experience the shear here on the first set, and it will experience the shear on the second set. Now this we call it the double shear stress. And in calculating the double shear stress, it will be tau equals to force over 2 times area, because the pin, it's been sheared on two positions, or on two on two positions. This would be the first position and the second position. Then we will be using this formula to calculate the double shear. Please make note of that formula. Okay, don't forget it. Make note of that formula. That's for double shear. Double shear, it goes hand in glove with this diagram that I just indicated. Now, we shouldn't limit our double shear to that diagram. Let's give you another diagram. Some of you, you did see that you did work with this diagram when you were doing your N4. You are having a shekel. This is a shekel. This is my funny shekel there. Then there's a pin in here. Then there's a hook in that shekel. There's a hook, right? Then it is tied to a rope. Then it experiences the force normal, the upward force. Now you would realize that this pin here, this pin will experience a shear here and a shear there, since they are pulling this material upward. Now, when you are given the statement, you need to read the statement carefully. Do they want you to calculate the stress on this pin, which is, under that shekel, or do they want you to calculate the stress on the shekel itself? If they want you to calculate the stress on the shekel, that means the shekel would be hooking maybe a big box. Then you will be calculating the stress here. This would be the single. But under this pin, it will be double. Okay? Please, you need to read the given information carefully so. Okay? When coming to the shear stress. Now, again under the shear stress, when you are given a flat metal plate like this one, you are having the thickness of the plate, okay? The thickness of the plate, then it has a hole. Now, in calculating the area of that hole, first you need to know how to calculate the area of that hole, or how to calculate the stress there. In calculating the stress there, it will be that tau equals to force over pi multiplied by the d. This d, it is the d for that hole there. Multiplied by what? By thickness, the thickness of this metal plate. Then you get what? The shear stress. Now in calculating the area of this metal plate, or it will be this formula here. In calculating, it will be area equals to pi d multiplied by thickness. If you are given this scenario, now this is the route that you will take. If you are given that scenario, double or single, it doesn't matter. Okay, that's what we will be dealing with here. What is it that we are supposed to know? We need to know how to calculate stress. It is force over area. We need to know how to calculate strain. It is change in length over L original. We need to know how to calculate those formulas. Okay. Now let's continue. If you are given a test piece like this one and there's a force applied, this material, like I said, will experience the change in length and the cross-sectional area. Now, before the deformation takes place, this material, it will undergo certain stages, of which you need to know how to plot you need to know how to label those stages. You need to know how to explain those stages. We said the first stage here, it is the limit of proportionality. This is the upper yield. This is the lower yield. Maximum, that's when maximum stress occurs. Maximum stress, then fracture. You need to know how to draw the stress and strain graph. You need to know how to label it. You need to know how to explain those stages. Okay. Now, this is the graphical part of it, of drawing stress and strain graph. You can be asked to draw the stress and strain graph analytically, meaning you will be given forces. You will be given forces. This is your force, it's in kilonewton. Then this is your change in length, it's in millimeters. Okay, you will be given forces. Force 1, force 2, force 3, force 4, force 5. Then you are given the change in length, 1. Now, you are told the SI unit is in millimeters. It means here you are having 2 times 10 to the power negative 3. It means here you are having 5 times 10 to the power 3. Now, you first have to calculate stresses. If you were asked to plot the stress and strain graph, if you are given that information, you then need to calculate the stresses and calculate the strain. From that given information, you will then be able to draw the stress and strain graph. Yeah? Now, in calculating stress, it is force over area. It means you will be given the diameter original. From there, you calculate the area. Then you will be given length original, the one that you'll be using to calculate the change. You will be given the length there. Now, after you've calculated your area, you can then calculate your stresses. How many stresses must you calculate? 1, 2, 3, 4, 5. You calculate your stresses. This is force 5 times 10 to the power 3 over the area that you would have calculated there. Then you get what? You get your stresses. I'm just writing there and giving you the picture. Then under your strain, can you see that I've written 39 megapascal? Under your strain, you calculate your strain. It is the change in length. The LO, let's say we are given the LO as 50 millimeters. It means it will be change in length over L original. It will be 2 millimeters divided by 50 millimeters. The mil and the mil will cancel out. Then you will get your answer as, yes, your answer would be 0.04. It doesn't have an SI unit. Now, let me give you a tip in drawing the stress and strain graph. After you've calculated your stresses, this is your stresses, this is your strain. Indicate under the strain. What is it that you need to indicate? It means you need to raise this thing, this answer to exponential form. Let's say we are raising it to exponential form. It will be -4. All our strains, it means they must be raised to exponential form. Okay, then you indicate here that my strains, they are in what? Exponential form. Then under your stress, you indicate it is megapascal. Why must you do this? This will help you in drawing your stress and strain graph, more especially in choosing the suitable scale. Now you are having your strain 1, it is 4 times 10 to the power -4. Let's say the strain 2, it is 11 times 10 to the power -4. This is your strain 2. When you choose the scalar, you will be looking at 11 and 4 and choose the suitable scalar. If you say 10 mil is to 5 strain, 5 times 10 to the power -4, then we know that when you plot your graph, it will be 5, 10, 15, 20, but using what? The 10 mil. It means from here to there it is 10 mil. From there to there it is 10 mil, but the values it will be 5, 10, 15, 20. Then when you plot your graph, you know that strain 1 it is 4. It means strain 1, it is 4, it will be here. Then strain 2, it is 11, it will be here. Strain 3, let's say it is 14, you know that it will be here. This will be easy for you to be able to plot the graph. Same thing with your stresses. You forget about 10 times 10 to the power 6. You leave the exponential one, then you focus on the whole number there. That's how you will make your life easy in drawing your stress and strain graph. This is how we plot our stress and strain graph. Then when we see this line, after we've drawn our stress and strain graph, we get to realize that this is what's happening. Then you draw the straight line. Where the tangent line occurs, that's where the Young modulus is. That's where the limit of proportionality would be. That's where Hooke's law would be applicable. From this region, that's where your Hooke's law would be. That's where the strength of the material is. Thereafter, the deformation starts to occur. From this point going forward, it is the deformation. Then they will ask you to determine the strength of material after you've plotted your graph. You will then use the stress that you got there. Let's say it is stress 3 and the strain, it is strain 3. Then in calculating your strength of material, obviously they want the Young modulus. It will be stress over strain. The true formula, it is the change in stress over the change in strain, because it occurs on the gradient line. But we always advise you that you need to take it with it should be stress 3 minus stress 0. Then it will be strain 3 minus strain 0. We know any number plus or minus, it is that number. Okay? This is how you will then calculate your Young modulus or the strength of material in that region. Now, secondly, another thing that you need to know, they can ask you to calculate the force graph. Now, we are having, this is your strain, stress, and your strain. How do we calculate the stress? It is force over area. How do we calculate the strain? It is the change in length over original. Now, they can ask you to calculate the force graph and change graph. It means instead of using the stresses, you will be given the stresses. You will be given the stress, you'll be given the stress, you'll be given the stress on the limit of proportionality. You'll be given the stress on the yield. You'll be given the stress on the maximum. You'll be given the stress on the fracture. If you are given the stresses, then you calculate the forces. It will be stress on limit of proportionality equals to force over area. You would obviously be given the area, then you make F the subject of the formula. Stress, limit of proportionality multiplied by area, then you get your force. Let's say this is your force that you have calculated. This is the force that you have calculated. This is the force that you have calculated. You come and calculate the change. Then you plot the force stress, the force change graph based on the forces that you have calculated. Force 1, force 2, force 3, force 4. Change 1, change 2, change 3, then you plot your graph. You plot your graph. They can ask you to calculate, to draw the strain graph or the force graph, then you join the dots. Then you join the dots. Then you put your ruler. Where the tangent, okay, that's where the strength of material is. Now, they can ask you to draw the stress and strain graph, or they can ask you to draw what? The force change graph. But the force change graph, you will obviously calculate it from the given stresses. I hope that makes sense. If it doesn't make sense, holler at me so as to explain even further. Now, let's look at this given example here. We are given the information, a tensile test to destruction carried out on a steel test piece of diameter 16 mm and gauge length. Now, this is the area that you'll be using to calculate the stresses. This one, area that you will use to calculate the stresses. This is the gauge length, LO, to calculate your strain. To calculate your strain. Because your strain, it is change in length over L original. Now you are given the L original, there it is 70. Now we are told that the load at the limit of proportionality, the load here, it is given as 68. We can then calculate the stress at that limit of proportionality. That is why the first question they are saying, calculate the stress at the limit of proportionality. It is stress limit of proportionality equals to force over area. Which area? This area. Area equals to pi multiplied by 0.016 squared divided by 4. Then you get your area. Then you are able to calculate the stress at the limit of proportionality. It is 68 times 10 to the power 3 divided by the answer of the area there. Then you get your stress at the limit of proportionality. Then question number question number 2, they want you to calculate the Young modulus of elasticity of the material. Now you can tell that the limit of this is where they want us to calculate what? Young modulus. That means here we need to calculate the strain. How do we calculate the strain? The strain, it is change in length, and of which it is given, divide by L original. Here's the L original. Here's the change in length. Based on the given information, there it is. We are given the change in length. There it is. Or the extension at the limit of proportionality. There it is. The extension. We are given the change in length. There it is. Then we are able to calculate the strain. The strain would be change over LO. This is my change. 130 times 10 to the power negative 6 divided by 70. Then I get what? Then I get my strain. Then from there I can calculate my Young modulus, stress over strain. Can you see that? Then they want us here, question number 3, they want us to calculate the yield stress. The yield stress, it is easy. If you are given such information and they didn't specify the load at the yield, we always assume that this load, if they didn't specify whether it is the upper or the lower, we always assume that load at the yield to be the upper, like I did here. Okay, it means the whole region here, it is under what? It is under 90 kilonewton. Then from there you are able to calculate the stress at the yield. It is force over area. Which area? The area that you would have calculated using that diameter. Then you get the stress at the yield. Same thing here at the maximum. Same thing at the maximum. Here's the force max. The area that we are going to use now here. The force that we are going to, the area that it is the smallest area. Check. Here's the smallest area. This is the area that we need to use there in calculating what? The maximum stress. Then they want you to calculate the breaking stress. Obviously, the breaking stress as well, it will be this and the force here at the fracture. Now, this can be difficult, good people. This can be difficult. This can be difficult, good people. This is how you tackle your stress and strain. I want to believe that these 2 videos will help you, good people, in covering your stress and strain graph. Then I will post solutions of these equations here. Let me give you a few seconds so as to take the picture of these equations here. Then later on I will post solutions of these equations. Okay, I hope these videos are helping, good people. If you need clarity, indicate in the group that say, can we then have an online class so that you can give us clarity on things that needs what? Clarity, good people. I don't want to leave you in the dark. I am here for you. Take a picture, look at them, take the picture of these questions. Okay, here's another one. Take the picture as well of these questions, attempt them. Okay, thank you, good people. I will send the solutions nonetheless.